I'm capable of doing, but what I hope to share with you today is, first off, okay, how do we take an analog signal and convert it? And what are some of the considerations we have to think about? And then we're going to go from there to, all right, everything today is using some kind of audio compression, some kind of video compression. How does that basically work? What are the main blocks that have to occur for that to happen? So that's pretty much the presentation today. And we're going to start out here. We've got an analog signal. I had a working. There we go. We've got an analog signal, and if we were to graph this in terms of amplitude and time, and in each one of these points we were to plot the signal, then we could make a numerical representation of this analog signal, no matter what it is. It's an analog something or other. There's a little problem with doing that. Now, here's this solid line is our original signal, and the dotted line represents each point essentially where we plotted it. Now, notice that this signal here is roughly half the frequency of the original. I'll get more into that in a minute. But the point I want to just bring up right from the get-go is that there's more to just plotting and assigning a number to an analog signal. So we're going to have to consider just what we need to do. Now, there's some basic steps in converting an analog signal to digital. The first one is represented here. This is called sample and hold, and if you want to draw a little capacitor to ground from here, that would probably be good, because what we're going to do is we're going to feed this analog signal in, and this switch is going to be toggled closed by these sample pulses here. And these sample pulses are a very short duration, and what it's going to do is basically produce discrete pulses at the output. And these discrete pulses are referred to as PAM, or pulse amplitude modulation. Now you're still in the analog domain with these pulses. They're discrete, but they're of a specific value, but they have not been converted to digital yet. So let's say this was an audio signal, and we push this through an amplifier and listen to it in some speakers, we'd hear the audio. And if we did the same here and amplified it and put it to some speakers, we'd hear audio still. Go with me on that? It's not digital yet.
If you drew that little capacitor and close your switch long enough to charge it to the appropriate value,
yes.
Then you open the switch, that capacitor is going to stay at that voltage.
It stays at that voltage for, and you bring up a good point that I wasn't going to get into too much. The value of that capacitor is extremely important, because you want the capacitor to charge up long enough to provide you with a nice little pulse there, but you don't want it. You don't want to step. Yeah, and so the value of that the quality of that capacitor is extremely important.
You burn it off with a resistor then?
Generally, the next stage impedance is enough.
Okay. the outputs, right?
Yeah.
Doesn't say as a step.
So this is,
So there may be a little tail off on the,
oh yeah, absolutely. I mean, if you've got a good enough scope to show it,
yeah,
you're gonna see that, yes.
okay.
Yes, and this will have a pulse width to it, obviously. But in general, when you're dealing with audio frequencies, say, below 30 kilohertz, and you go and you have circuitry that you can discretely scope, you're going to see pulses like this. Now, these pulses have a specific value associated with them. And what we need to do next is we need to take that value and convert it to an actual binary number. And that's the actual step into the digital domain. It's called quantization. So you can see here we have a +1, and here the example is a 4-bit number, and we're converting that into 0001. And here the value is 4, and we're converting it to 0100, etc. And there's many chips that are available that do this, and will feed you out a binary output of zeros and ones. And in most cases, there's some kind of coding involved here. So for example, here we have negative going pulses, and to show a negative number in binary, we have to do something like gray code or
Two's
something.
complement?
Yeah.
That's what you use there, two's complement, right?
Or, yeah, this is two's complement, exactly.
Oh, there it is, it says that.
Yeah. And this, if it was compact disc or any kind of TCM audio, would be also encoded in NRZI, which is called non-return to zero inverted, and so on and so forth. But that's kind of beyond what we're talking about today. So basically then we have the sample and hold process, which produces discrete samples that we can then convert to a binary number. And that's what we're showing. And this is shown as a serial stream, but obviously it can be output as a parallel stream as well. Now, using a basic digital audio block, we've got our audio coming in, and generally the audio, well, for compact disc purposes, it's considered to have a bandwidth of 0 to 20 kilohertz. And for some of your newer stuff, it's considered to have a bandwidth between 0 and 22 kilohertz. I don't think there are too many in this room that can hear much above 14 kilohertz anymore, but anyway. So now here's our little capacitor drawn in right here. And anyway, so we come into our sample and hold circuit, and at this point we have our pulses. We go into the actual conversion process where we take the value of each one of those pulses and we convert it to a binary number. In this case, we're just showing 4 bits. Actual digital audio is a 16-bit word. So that means that you have, well, I'll get into that in a second, a lot of levels. And then the output has to go into some kind of modulation generally. If you're going to store it on a CD disc, you're going to use something called EFM, 8 to 14-bit modulation. If you're going to put it on some kind of digital tape, you've got another form of modulation. But at any rate, some form of modulation is used for the zeros and ones, and then you've got a storage device involved. For purposes of our discussion today, we'll say that's a compact disc, because we're all familiar with it. When you play back your disc, you have to demodulate the signal, and in a compact disc player, that's called an EFM demodulator, where we actually take a 14-bit word and we convert it back into an 8-bit word. But the bottom line is that we get a string of zeros and ones that represent the original signal, and we feed that into a digital to analog converter, and guess what this guy puts out? It puts out pulses. And we call those pulse amplitude modulation. And at this point right here, if you were to tap the signal, amplify it, and listen to it, you would hear audio. It might be a little rough, but you would hear audio. And then we take these pulses and we put them through a sample and hold circuit, which is timed to the pulses, and this is where the time constant is longer. And then we push this through a low-pass filter, and we get a very clean audio output. So if you've got a sine wave coming in here, and you put your scope here, you're going to see a nice sine wave. And if you have a fairly good chipset, you're not going to see any kind of artifacts associated with the signal. So that's your basic conversion process. Now here we've been talking about converting an audio signal. Well, it could have been a video signal. It could have been a signal that corresponds to variation in temperature, variations in voltage. It doesn't matter. The whole concept is very similar. Now, there is one fly in the ointment, and this has to do with how often we sample the signal. Now, in a former life, I used to remember all the little details about this, but anyway, there was this guy called Nyquist that worked for Bell Labs back in the 30s, and he was trying to figure out how to send Morse code over telegraph wires faster. And in the process, he developed something called Nyquist's theorem, which basically says that for you to get an accurate reproduction of your signal, when you digitize it, you must sample it at least 2 times as fast as the maximum frequency. So, if we're talking about compact disc, then the maximum frequency that we are interested in is 20 kilohertz. Well, 2 times 20 is going to be 40 kilohertz, and then we need a little fudge room, and so the actual sample rate for a compact disc is 44.1 kilohertz, and it yields us an effective frequency response of 0 to 20 kilohertz. Now, so if we consider this as an audio signal being generated by a sweep generator that's sweeping, say, between 0 and 20 kilohertz, and we put a spectrum analyzer on the output, which is going to give us an output in the frequency domain, we would see an output that would go from 0 to 20 kilohertz. Well, we're going to sample and hold that, develop our pulse amplitude modulation, And then in the process, something that is very similar to AM modulation occurs. If this is our sample clock right here at 44.1 kilohertz, we will develop sidebands, a lower sideband and an upper sideband that will correspond to our maximum frequency plus or minus,
Some of the difference.
yes, the clock frequency. So, in other words, the lower edge of the lower sideband right here would be 44.1 kilohertz minus 20, or 24.1 kilohertz. And the upper edge of the upper sideband would be 44.1 kilohertz plus 20 kilohertz, or 64.1 kilohertz. And so if you looked at the output of compact, one of your first generation compact disc players with a spectrum analyzer, you would see this kind of display. Now, what if your sample clock or sample frequency is not 2 times as fast? Well, if it's not 2 times as fast, let's see, all right, if it's exactly 2 times, then notice that the lower edge of the lower sideband comes butt up against the maximum frequency you're interested in. Not a good idea, because in the real world, you need some fudge room, right? And if it's less than that, then you have the lower edge of the lower sideband impinging into your signal, and this gray area is called something very specific, is called the alias. So if you looked at buying, you know, a digital storage scope or something like that, the one of the specifications would be your alias spec. Now, this, if you were to, if this was audio and we had an alias problem, this would result in a low frequency distortion. Would be very, very bad, low frequency distortion. So anyway, the idea is you really want to have some fudge room here. Otherwise, your low-pass filter, remember we showed in the previous slide, the output is a low-pass filter, right here. That low-pass filter has got to be so sharp that it'd be very expensive and difficult to build.
Yeah, I think I read where that low frequency distortion, where you can't get an accurate replica of the original waveform, is like walking into a room with mirrors, where the mirrors are not large enough and you can't get a full reflection of the image as you're walking in, and it's just total distortion.
That would be another way to look at it. And since we're going to move on in a few minutes to video, we have the same issues with video. If we don't sample the video at a high enough sample rate, we're going to introduce distortion in our video, and it really obscures the video, you know, what you're trying to reproduce. Now, in addition to the fact that you need to sample your signal fast enough, you also need to assign enough bits to each sample. And what we're showing here is this. This is referred to as quantization noise or error. Let's say we sample right at this point. Notice we're kind of right in the middle. Is it a 1 or is it a 0, right? Well, that's the question. Well, here the maximum error is gonna be what? Half a volt. Give one way or the other. Now, obviously, if we're talking audio, you know, half a volt one way or the other just wouldn't cut it. But kind of what's interesting, remember the way you count in binary is 1, 2, 4, 8, 16, 32, 64, 128, 256, etc. Every time you add one bit, you double your resolution, right? So here, we're going to add one bit. Now, instead of having 4 bits, we have 5 bits. And now we've halved the maximum distortion. Now, instead of having half a volt of distortion, we have a quarter of a volt. And if we keep on adding bits, why that error or distortion is reduced. Now for audio, we assign almost always 16 bits, which translates out to 65,536 little steps. And interestingly, your ear is much more sensitive or more difficult to fool than your eye. And so with audio, we need 16 bits. With video, we can get by with 8 bits just fine. So, and as you're going to see in a little bit, when it comes to like the color in a picture is almost unimportant. Color has no detail in it whatsoever. Well, anyway, this is giving us an idea of how a compact disc player block actually looks. We have a left and a right input. We go through our AD converter, and this gives us a data rate of 705 kilobits per second per channel, or 1.4 megabits per second once we combine it. In other words, we'll have they multiplex the signal. They'll have a sample of left, a sample of right, a sample of left, a sample of right, like that. We go into a digital processing block where we add our error code, which is a form of Reed-Solomon error correction. And that jacks up the actual data rate quite a bit. And then your storage is the actual disk. Now, that means then that uncompressed audio, like on a CD player, has got a data rate before error correction of 1.4 megabits per second. You're generating a lot of bits, right? And if you got to move these bits over the internet, not a good thing, right? Or if you want to store all of this on a flash drive or something like this, that data rate is just too high. So we need to have some way to compress it, right? And that kind of leads us into our next subject, which would be audio compression. Now, both audio and video compression make use of extensive studies of how people hear and see. And those are sciences all unto themselves. But at any rate, for purposes of a Saturday afternoon chalk talk, we're going to point out a couple main things about the way people hear. First off, there's something called a threshold of hearing. Here's our audio signal that we're interested in, this signal right here. Now, depending upon your age, anything that falls underneath here guess what? You're not gonna hear it, yeah. Now, yeah. So younger folks have got, they can hear a much lower threshold, but there's an average threshold of hearing that applies to all people, right? Whether their hearing is super good or not good, right? And so any of these signals that fall underneath this threshold here, guess what? We're gonna throw them away completely. We just toss them. Now, what does that do? Well, since you are throwing them away, do they occupy bits in storage? No. And so that's the one thing that
Then you get into that variation in your time when your samples occur, right?
yes, and that is called the critical zones of hearing. Now, here, notice that we've converted the signal, and we're going to look at this in a little more detail when we look at the video. But notice that we're in the frequency domain here versus the time domain, which means that we have had to have done a Fourier transform to go from the time domain to the frequency domain. But these frequencies, and notice this is low frequency and moving up in frequency here. The level at which you can hear varies, right? And that has to do with the way your cochlea and all of the inner workings of the ear respond. And that creates so-called critical bands, where there are some frequencies that people process more carefully than others. So guess what we do with the frequencies that you don't process much? We either throw them out or we assign them fewer bits. So this is how we can take an audio signal and first off throw away a whole bunch because you can't hear it anyway, and then based on the frequency of each sample, we will either assign it more or fewer bits. Everybody comfortable with that idea? It's done on the fly, yeah. So when you come out of your AD converter, right? You've got your signal in the digital domain. The first thing that you do is you go from the time domain to the frequency domain. And once you're in the frequency domain, then the signal is evaluated for its frequency components. And you're going to see that and this is done on the fly. It requires very fast processing, even in the audio domain. But in the video domain, we do something very similar. We then look at the resulting output, and where we have repeating patterns, and this is something called Huffman encoding, which is basically anytime you have a long repeating pattern, you replace that repeating pattern with just a flag of a couple of bits. And so when you zip up a file on your computer, right, this is what you're doing essentially. This is like pkzip right here, or winzip. So now this does not throw away anything. This does not throw away anything. But what it does is it looks at the data stream, and wherever it can reduce it, it reduces it. And the final slide on the audio gets a little more into the fact that we're going to evaluate our samples in the frequency domain. And we can decide based on what kind of pattern it is, or frequency more specific, how many bits we're going to assign to it. A lot of bits, because the brain is going to, you know, really scrutinize that frequency, or very few bits. So that's the way, in a nutshell, from a very broad stroke, how MPEG audio compression works, or 8-track audio compression, or any of these audio compression schemes that are out there.
How much computing power do you need to do this audio compression?
If you consider that your basic sound card is capable of doing this, that would give you an idea. And of course, on the playback side, you don't need near the same processing power, because you're only working with what's left on the playback side. But on the record side, yeah, it takes a little. But I mean, this is an i3 with a crappy sound card on the motherboard. It'll do just fine. So.
Kind of depends on
You're
how much time
recording
you have, right?
on your PC here, is it being compressed to be done by the central processor, or is it be doing it on the sound card?
Some of it's done by the sound card, and some of it's done by the CPU. Now, they make sound cards that do it all, and it's totally offloaded from the main CPU. So yeah, it's pretty wild.
Doesn't really depend on how much time you have. I know quote unquote, ripped from a CD to MP3s on a 486.
Oh yeah.
You know, it just maybe takes 10 minutes or something to do a song, whereas, a new machine would do it in 10 seconds. But if you're talking about encoding it and doing it live, then it'd have to be able to keep up with that.
And that's a good analogy. But the one thing you have to keep in mind is when you rip from a CD to like an MP format, you're already in the digital domain. So
Part of the work is done.
part of the work is already done, right? Yeah, but you're right. An old 486 or even a 386 could do it. The early Sound Blaster 16 cards, you could get them to work pretty good. So, well, I've got 10 minutes to tell you about video. All right, video is kind of interesting because first off, when we think about video, we normally think about color video, right? But most of us remember black and white television. And then color came along, and the thing that you have to remember about color TV, regardless if it's the old analog or the new digital, is that it's made up of, you're taking three colors, red, green, and blue, and you are going to formulate a monochrome signal out of that, and also a color signal out of that. Now, how do you formulate a monochrome signal? Well, your monochrome signal is made up of approximately 59% green, 30% red, and 11% blue. So those are your three colors. Now, if you've got any of these color cameras, video cameras, they're going to have three color signal outputs. And the very first thing that happens in just about any video camera is that you take your red, green, and blue outputs, you develop your black and white signal, which is called the Y signal, or luminance signal, and then you generate a signal called red minus y, or r minus y, and b minus y. There is no g minus y, because if you have y, r minus y, and b minus y, you can generate g minus y and convert back to your original red, green, and blue. Now, the other thing you need to know about video is that all of the detail, all of your sharpness in a picture is not in the color. It's in the luminance signal. It's in the luminance signal, or the Y signal. So anyway, what they're showing here is that coming out of your camera, you've got red, green, and blue, but then immediately you convert it to Y, R minus Y, and B minus Y. So 1 pixel would be comprised of those 3 components. Now, think about this. If you have a nice HD set at home, a 1080 set at home, you have 1920 pixels across, 1080 rows down, multiply that together, and then multiply that again by 3. You have over 6 million elements on the screen that have to be addressed, all right? Over 6 million elements that have to be addressed. Here we're not, the example is standard definition, which is 720 across and 480 down.
That one 525 down.
Pardon?
Wasn't it, didn't used to have 525?
525 included the blanking area. But if you strip out the blanking area, you're left with 480. So that's another discussion. But yeah, you're quite correct on that. All right, well, again, the compression process involves, first off, selective sampling. Then we do a discrete cosine transform, which is abbreviated DCT, and that's actually a Fourier transform where we go from the time domain to the frequency domain, because we're going to evaluate everything in terms of frequency. Then we're going to do something called predictive and motion encoding, which has to do with spatial and temporal evaluation. And finally, Huffman encoding, that should be H-U-F-F, not Hoffman, and that's like zipping the file. Now, let's consider what happens at the local TV station. Even in the days before HD, the TV station recorded in what was referred to as 422 video. And basically what that means is that for every sample of Y, or for every 4 samples of Y, so here's a sample, here's a sample, here's a sample, and here's a sample, they only took 2 samples of B minus Y, R minus Y. What happened to the other 2 color samples? They threw them out. Never used them. And that's back in the analog days. So right from the get-go, we threw away 50% of our color signal. What's that tell you about the importance of the color signal? It's not that important. Well, then came along DVDs, and we needed to throw out even more. And so here, for every 4 samples of Y, notice we're take 1 sample of R minus Y here and 1 sample here, but no B minus Y. We wait till the next line comes along, then we take the B minus Y samples.
So when they, in the end, they basically interpolate all the holes?
Yeah, Yeah, more or less, that's a way, you could think of it.
Resistance.
The bottom line is here is that we threw away 75% of our chroma signal, but notice that we kept all of our luminance signal. All of the monochrome signal is kept. Now, that's selective sampling. Now, once we've sampled it, we're going to AD convert it, and then we're going to take the picture frame, which is converted into numbers at this point, and we're going to, in the case of a standard definition signal, we're going to break it up into 5,400 blocks, and each block is made up by an 8 by 8 pixel block. Or, in other words, there's 64 pixels in this block here. Now, we are going to then look at the frequency components of that 8 by 8 block, and we're going to push all the low frequencies up into a corner. Basically, it's like we took that matrix and rearranged it. And so all the low frequencies are grouped together and all the high frequencies are grouped together. And then at this point, we decide how much high frequency we want to throw away.
This picture before this one, you're talking about dividing up the screen, which is in the spatial domain.
This is kind of a hard concept here because we are in the digital domain at this point.
But are the two dimensions here in space or in wavelength?
There's okay. So let's first consider that we are number one in the digital domain, and each word in our frame data corresponds to a specific pixel in the spatial domain.
Okay.
And now we are going to subdivide this all up into these smaller blocks for evaluation purposes.
Now, to get to the next slide, are you going to take the two-dimensional Fourier transform of that block?
This block, yeah, this block is the data in this block here, and this is confusing because each block represents a word, a digital word, which represents the frequency of the sample.
So those little blocks in your 8 by 8 block are not pixels.
They represent a pixel. They represent a pixel.
That has a spatial coordinate on the screen.
Correct.
So how do you jump to frequency?
We did a Fourier transform right at the get-go. But the spatial position in terms of where each one of those words is located is retained. And that's a whole kettle of fish on its own self. Yeah, that's excellent question. Excellent question.
Must be a physics guy.
Well, the physics guy is kind of mixed up at the moment.
So I'm being that my time is about out here, or actually out, I'm going to kind of just finish this up. The bottom line is here is at this point in time, we're going to decide how much high frequency we want to keep or throw away. And when I say throw away, I mean it's gone, non-recoverable. And so if you've ever looked at some of this, your cable TV high definition programs, some of them are sharper than others. Well, you know, Comcast or the Time Warner or whomever makes a decision about the amount of compression they want to apply to the signal, and based on that, you know, they can squeeze the signal into a smaller bandwidth.
This is why sometimes on-the-air signals are sharper.
Absolutely. Oh, absolutely. Because the on-the-air signals, they're compressing, but they always have more or less a fixed rate. Whereas the cable companies, you know, if they need to put up 6 more games on a Saturday afternoon, they gotta get the bandwidth from somewhere, so they compress the signal more.
That's the movies.
All right, now, the final thing is, when we're talking MPEG and most other types of video compression, what we're going to do is we are going to compress the signal by both looking at the spatial and the temporal parts of it. Now, when we say spatial, that's your space, right? So I want you to think about a sailboat on Lake Minnetonka on a clear blue day. The sky is blue all over, right? If we take a sample of the sky over here, it's going to be pretty much the same as the sample of the sky over here, right? So guess what we're going to do? We're just going to take a sample of the sky here, and every time we need to plug in for the sky, we're going to say, use this value, all right? That's spatial redundancy.
That's why the TV looks better than out the window, right?
All right, now let's talk about temporal redundancy. That's changes over time. Now think about your newscaster. If your newscaster is, you know, sitting there, what's changing? His mouth, right? Yeah. So here they're showing. Here they got a kid with a skateboard or something, right? And in the next frame, the only thing that changes, okay, he raises his hand to wave, right? So guess what we're only going to bother to keep? That. Or here, this plane is going from here to here. Well, if we sample the plane here, then all we have to do is plug it in as its position changes. We don't need to record that plane every single frame.
So,
right?
So that's why some of the parallax stays the same as the plane goes by.
Well, there's all sorts of stuff that goes on with that. I don't know. Anyway, this gives rise to the fact that when you do MPEG compression, you're going to take a group of frames, generally at least 15, but it can be more than that, frames. The first frame is your reference frame. You're going to basically record everything in that frame, and it's going to require the most data. But then, as your subsequent frames come along, we're going to look at what happened before and after. And we're going to develop 2 other kinds of frames called P and B frames, predictive and bidirectional frames. And these frames just have what's different about it. And so basically you go from these, you can go from this enormous frame rate if you have no compression. And if we had more time, we could work out some numbers. I mean, it's just staggering the number of bits that are generated to something that you can, you know, record an HD movie on a thumb drive. And it looks damn good. So anyway, guys, my time is up. I thank you for your kind attention.
Thank you very much, Steve.